Okay, hello everyone, welcome back to another video. I'm sorry that it's been a while since I've last uploaded. I've had all sorts of exams and academic stuff going on, but we're back today considering a really interesting coin tossing problem. And it asks, if I toss a coin, what's the expected number of tosses that I'm going to have to make to get n consecutive heads? And with interview season coming up for all sorts of jobs in data analysis or statistics or for universities, this is a really useful problem to be familiar with. So I think the simplest case to consider is when n equals 2. That means what we're looking for is the expected number of times I'll have to toss a coin to get 2 heads in a row. And we can consider the probability tree for this to aid our understanding. So instantly we can either get a heads or a tails. And again, after having one head, if we do another toss and get a second head, we're done and we don't need to keep tossing. Otherwise, we get to a tails again and we've lost that head and we're basically back to square one. And that idea of being back to square one is exactly how we solve this problem. See, at the beginning, before I toss anything, it doesn't matter what I get next because I don't have a head before me. I've got to have a head before me and get a head after to meet this condition. So if I toss a tails, then all that's happened is I'm back into the state that I was before. I'm completely reset. So the expected number of tosses to get 2 consecutive heads from this position should be exactly the same as the expected number of heads from this position, or equally from this position, because in either of them we lose that head we've accumulated and we're back to looking for 2 consecutive heads. And so when we're considering the expected value, we'll consider first the branch where we get heads, and just as a reminder, the expected value is x times the probability of x being that value. And in the case of heads, it's taken us 2 throws to do that, so that's the value of x, and the probability of that occurring is a half times a half because our coin is totally fair, which is going to give us 2 over 4, which we can just write as a half. And then for the other 2 parts of our diagram here, either where we get a tails after a heads or where we start off with a tails, we can express these parts of the sum in terms of the expected value. Because there's a half probability of getting a tails here. And then the expected number of throws is going to be exactly the same from our position here. But of course, from the origin, from where we started, it's actually 1 more because it took us a throw to get to this tails in the first place, which means in our sum, we're going to represent that as a half times the expected value of x plus 1. And again, for our branch over here, there's a 1/4 chance of this occurring. And in this position, the expected value of x should be exactly the same, but it's taken us 2 throws to get there, which means we have the expected value of x plus 2. And now, using this equation of the expected value of x in terms of the expected value of x, we can rearrange to solve. So we get expected value of x is equal to a half plus a half the expected value of x plus a half plus a 1/4 the expected value of x plus a half. And with a bit of rearranging, that's going to give us that a 1/4 times the expected value of x equals 3 over 2, and therefore our expected value is 6. And I think that's a really satisfying ending to the question. It kind of does feel right. It's one of those ones that you can't really go off of intuition fully though. I think that a solution like this is really neat. But what's even more important is that there's nothing in our solution there that is specific to 2 consecutive heads. There's nothing to say that we couldn't do that for 3 or 4 or 5 or n. And if we consider the tree for n consecutive heads, we'll have a reset tails here, and then a heads, and then a heads, and then a heads, and at each branch we'll have the possibility of a tail that resets us back to the state that we started in. Which means that we can write the expected value first as the weighted probability of getting just heads, and of course that's going to take us n tosses and has a probability of 1 over 2 to the n of occurring, so that's the first part of our expected value. And then we're going to want to add, well, a half times the expected value of x plus 1, as we did before, plus a 1/4 times the expected value of x plus 2, plus an eighth times the expected value of x plus 3, going on and on and on, which we can capture with some sigma notation as the sum from k equals 1 to n of the expected value of x plus k all over 2 to the k. And a big part of solving this problem is going to be cleverly manipulating this sum over here. So let's make some space and consider this sum, and we're going to do it in purple, and we can return to our original formula at the end to find our answer. So we're considering the sum from k equals 1 to n of the expected value of x plus k over 2 to the k. And of course we can expand this out as the expected value of x times the sum from k equals 1 to n of 1 over 2 to the k plus the sum from k equals 1 to n of k over 2 to the k. Now this sum over here is quite simple. Many of you may have seen before the proof that a half plus a quarter plus an eighth going on to infinity is equal to 1. And it can be shown geometrically, it's a very common way to show it, as by considering a square of side lengths 1. And that's because when we add a half and then a quarter and an eighth and a 16th and we go on continuously, you can see that we will eventually approach a full square of 1. But we can also get something else out of this when our sum isn't to infinity but is instead to n. Is that, let's consider this case where we've got a half plus a quarter plus an eighth plus a 16th, so n must be equal to 4. What that leaves us with is an almost complete square, but missing 1/16. In other words, it's 1 minus 1 over 2 to the 4. And if you consider the geometry of that, we can generalize that idea. And that's going to tell us that the sum from k equals 1 to n of 1 over 2 to the k is equal to 1 minus 1 over 2 to the n. And the way to imagine this is that it's just that square with the missing chunk taken out of it. And so of course that makes this part very easy to evaluate. We know that that's just going to be the expected value of x times 1 minus 1 over 2 to the n. But this sum here, that's still going to take some more thought. Now we're going to use a really helpful method, in my opinion, for stats. You can use it in the geometric distribution in one of my other videos as well, and that's going to be diagonalizing this sum. So when k is equal to 1, we're going to have a half. When k is equal to 2, we're going to have 2 quarters. When it's equal to 3, we're going to have 3 eighths. When it's equal to 4, we're going to have 4 16ths. And I hope you can kind of see the pattern that we've got going here. It's that we've got a kind of set of diagonal sums that are expanding off n times, and we're going to consider each row, and that's going to help us with our calculation. So actually let's just undo this for now to make a bit more space. And if we consider the first row, well, we already know that that is just 1 minus 1 over 2 to the n. And now let's consider the second row. Well, that is just our original shape, but we don't have to consider this first half over here because we don't have it. So instead of being 1 minus 1 over 2 to the n, this is just going to be a half minus 1 over 2 to the n. And then it's going to be a quarter minus 1 over 2 to the n. And we're going to keep going like this until we've got 1 over 2 to the n minus 1 minus 1 over 2 to the n. Now this basically holds our answer. We've just got to consider the individual pieces. So here we've got 1 plus a half plus a quarter all the way up to plus 1 over 2 to the n minus 1. And that is 1 plus the sum from k equals 1 to n minus 1 of 1 over 2 to the k. And we know that this is 1 minus 1 over 2 to the n minus 1, which means that these circled parts of our sum together make 2 minus 1 over 2 to the n minus 1. And then all we've got left is n subtractions of 1 over 2 to the n. So we can write that as minus n over 2 to the n. And that is our really tricky sum, evaluated quite neatly with a really interesting method there. So let's write out everything we've discovered. We've discovered this is equal to the expected value of x multiplied by 1 minus 1 over 2 to the n plus 2 minus 1 over 2 to the n minus 1 minus n over 2 to the n. And now we've got that recursive kind of self-contained equation that we wanted. Now, not forgetting our n over 2 to the n that we had from our tails of just instantly getting consecutive heads, we'll return back to our equation, having now evaluated the sums, with this kind of big expression over here. And the first thing you might notice is that we've got an n over 2 to the n here, and we've got a minus n over 2 to the n here. So instantly, that's a plus minus going to cancel out. That gives us the expected value of x being equal to the expected value of x minus the expected value of x over 2 to the n plus 2 minus 1 over 2 to the n minus 1. And again, we can subtract the expected value of x on both sides, and we can add this expected value of x over 2 to the n onto the other side. And let's make some space to write what that gives us up here. So that's going to tell us that the expected value of x over 2 to the n equals 2 minus 1 over 2 to the n minus 1. And now all we've got to do is multiply by 2 to the n on both sides, which is going to give us that the expected value of x is equal to 2 to the power of n plus 1 minus 2 to the n over 2 to the n minus 1, which is of course just 2. So there we go, that is our general formula in terms of n. We can check if it works for the case n equals 2, which is the one we worked out before, and it does because it tells us the expected value of x would be equal to 2 to the 3 minus 2, which is of course 6, but now we can generalize this for any value of n. I hope you found this interesting. I thought the sum and the way we evaluated that was particularly satisfying, and as we're approaching 5,000 subscribers, I thought it would be a great idea to do 5 days of consecutive uploads. So as soon as we hit that milestone, I'm going to try my best to pull together all of the ideas I've been coming up with over the last month and put out a really nice quick-fire series on some great integrals and other summations and math-style problems. Hope you guys have enjoyed this video, and I'll see you next time. Bye.